Here we go. We have a question LRU cache. So we need to design a data structure. So pay attention, we need to design a data structure that works like a LRU cache. Here cap denotes the capacity of the cache and Q denotes the number of the queries. And query can be of two types. First one is the put query. So it will pass x and y. So we need to set the value of the key x with value y and get x. So it will get the corresponding value of x. If there is no value present, we need to return. If there is no key present, we need to return -1. The LRU cache has two methods, get and set, which is defined as follows. Get key, it will return the value of the key if it is already exist in the cache, otherwise -1. And the second method is the put. If the key is already present, update its value. If it is not present, add the key value pair. If the cache reaches its capacity, it should remove the least recently used item. So that's why it is called LRU, least recently used item, before inserting the new item. In the constructor of the class, the capacity of the cache should be initialized. So in the constructor, the capacity is initialized and we have two functions, get and put. And it is given, it will look like this. So let's take this query. So we have capacity of only two items. So first it will put 1 with value 2. Then again put 2 and value is 3. Then again put 1 with value 5. Then put 4 with value 5. Then put 6 with value 7. Then get 4. So I will write it here. Yeah. So get 4. Then 1, 2, then get 3. 1, 2, then get 3. So now let's say dry run this. So what we need to do? First we will put 1 with value 2. Then this is our first item. The next item occurs. So the value is 2. The key is 2. The corresponding value is 3. So it will put ahead of 1 and 2. It will put ahead. The reason being, the 1 and 2 is now least recently used. It is the latest recently. So you can visualize it like this. Then we have 1 and 5. So we already have 1. So we need to just update its value. So update its value, and this item will now come ahead. So this is the latest recently used 1. We just updated its value. So whenever we call set function or get function, it will be latestly used. Then we have 4 and 5. But our data structure reaches its capacity of size 2. So we're gonna remove the least recently used item. So it will remove least recently used item. Then it will add 4 and 5. So this is the latest value. Then the next item is 6 and 7. It will again remove least recently used and put 6 and 7. Then it is accessing 4, but 4 is there. Yes, 4 is there. So we will return 5. Let's check out. Yes, we have 5. Now it is latest recently used. So 4 and 5 will come ahead. 4 and 5 is now the latest value. Then we have 1 and 2, but 1 and 2 we don't have enough capacity, so we need to remove the least recently used. Then we're gonna add 1 and 2. then it is accessing 3, but 3 is not there, so we will pass -1, we will pass -1, and this is the answer. We need to return this and this. So whenever this get or put is called, we need to just set the value. So for this, if you observe what we need one or two things. First of all, we need a connection, so like this, so it will create a list. So suppose we need to insert new value, so it will be inserted on the front. So 79 is inserted on the front. This is now our latest value. Then what's the next thing? If let's suppose we are getting a value, we are accessing a value. So let's suppose this is the accessed value. So I will just remove the value from here and add on the front side. So the now linked list will look like this. So first of all, this is a linked list, this is a connection, and this is the head, this is the tail. So let's suppose we want to insert a new value, but our capacity is only 4 items, so we need to remove item. So we will remove the tail value. This is the least recently used yes, LRU. According to LRU, we will remove this value, and then we will add one value, so it will be added on the front. So it will be added on the front side. So let's suppose the value is 4 and 5. It is added on the front. So this now becomes the head. So we are aware of this. Then we need to access. We need to access. So we're gonna use map. So it will store key. Key is our integer. Then this is a node. So it will create data structure like this: integer and node. So we can easily detect whether a node is present with the corresponding key value, if it is present, we will directly access that node, and if it is not present, we can easily check if map contains the value or not. So now let's do a dry run. What things we require? We require a list. We require a linked list. So initially we have this data. So this data is not there. So we will add this data. How we will add this data? How we will detect whether this is our first node or our last node, or what's the position of this node. So before adding this value, I will create a value -1 and -1, -1 and -1. So this is my head, this is my tail, tail next is this, head previous is this. Why do we require doubly linked list? I will tell you. We require doubly linked list for this approach. So we have doubly linked list. So we have I hope you are already aware of doubly linked list concept and how we can create a doubly linked list. So let's suppose we have this node, so we need to add it here. So we will add after the head node. So in our doubly linked list, we have some functions. What function do we require? So now let's go to the code. So first of all, we have a node key data, and we also have next and previous pointer. So this will behave like doubly linked list. So let's create a doubly linked list class. So we have doubly linked list head and tail, and we have a constructor for this. We will create head and tail. Head previous is now tail previous is now head. So I hope you are very clear to this point. Then we need to add a function add to head. So let's suppose we have this node and we want to add it here. So yes, we require add to function, and we also require one more function. So let's suppose this function will work, and we have added a node. one with value 2, it will look like this. It will look like this. Head and tail will not change. Head and tail will not change because this is our head position, this is our tail position, this is our head node, this is our tail node. So that's why it will not change. And in the map itself, we will append the key is 1, and we will add a node. We will add a node. This denotes this node. So I think this video is going to be lengthy, but bear with me, you will get it. This question is very hard, I know. So pay attention and you will get it. So we have add to head function, remove from tail function. Remember, when we reach its size, we will remove a node from the ending side, from the tail side. So we have this function and remove a particular node. So this function will remove a particular node, and so actually this will remove from tail, and this will remove from any particular position we are passing a node. How this is useful? So let's suppose we have a linked list. We created a linked list, and we want to put a new value. So we need to first check if the value is already there or not, if the key is already there in the linked list or not. If a key is already there, so let's suppose we have this 2 and 5, 4 and 6. So we need to put 2 and 7. So we need to check if the value is already there or not. So using the map, we can find out the value is there. Yes, value is there. But we also need to remove this node. Why we need to remove this node? Only then we can add it on the head. So we need to also require a function that will remove a particular node from its position. And I think, yeah, that's enough. So now let's build the approach. How can we add a particular node on the head side? So let's suppose we have -1, we have -1. This is our head, this is our tail, this is our linked list, and we got 2 and 7. So we want to add it here. We created this node, this is our node, and we are passing yes, we are passing our node. Yes, we are passing. Then what we'll need to do, we need to add here, so head next is tail, or if we already have a linked list, it will also work. So let's suppose this is our head, and we already got some values here, 1 2 4 5, -1. This is our tail. So we need to add here on the head side, or add it here. So how we gonna add it? Here or here? So we have this node, so this position will be on the head side. So what I will do, this is our node. So node previous will point to head previous. Node previous will point to head previous. So we got 2 7. So what I am saying, node previous is equal to head previous. So it will connect it like this, then node next will be head, so it will look like this, and just remove other connections. So this is our insertion, and then what we'll do, so let me erase this part. This is our node next is this, or node next is this. So it's a node previous, this is previous, node previous is this, so node previous next, so node previous dot next will point to node. So what I mean is, remove this node, and it will point to here, and node next, which is head, So you can write it head dot previous is equal to node. So head previous is now pointing here, is now pointing here. So head previous will now will be point to here or here. This is the head previous, and we have successfully inserted this. So let me show you the code. So first node previous will point to head previous, node next, and node previous next, next previous. This is the insertion part. So we have inserted, so we have this this linked list. So we have inserted a new node. So first let's complete the doubly linked list functions. Why this function is important? So it will be important when we implement our data structure. Then the next function is remove from tail. So it is pretty simple. Remove from tail. So tail previous is this. We need to disconnect this. Actually tail previous initially pointing to this value, so we need to just reinitialize this pointer. So tail previous will now point to no, this is next. Tail next will be tail dot next, as simple as that. So it is now pointing to this. Tail next previous, tail next dot previous will now point to tail. So we have this and this. So it is working. This node, this particular node is never traversed, we will not visit that node any particular time. So this function is pretty simple. Remove from tail, and we need to return also. We need to return the value also. So we have some node here. So node this is tail next is our answer. So first initialize this, and at the end return your answer. So as simple as that, as I have written here. The code is pretty similar. Then the next function is to remove from any particular point. Remove a node from in between the list. So let's say 5, 6, and we have -1, this is your tail, and we need to remove a node from here. This is your node. Then we have this node, its previous pointing to this, its next pointing to this, its previous pointing to this. We just need to disconnect this. So actually this will be no useful when we directly implement this node and this node. So now it will be of no use. We will never traverse this node, we will never traverse that particular node. So you can write this code. It is pretty simple. So node previous, which is this node or any particular node, we don't care, dot next, its next is now pointing to this node, but we need to reinitialize this. It will point to node previous, node next dot node next. So it will point to this node previous next is equal to node next. Yeah, so this is your node, not this or this, not this. So actually it will look like this. Yeah, so node previous next, then this node previous. So node next previous will point to node previous. So it will look like this. We will not traverse this node, and yeah, so we have removed this. Okay, Till now we have only done the doubly linked list part. We have not built our data structure. Our data structure will contain a doubly linked list and a map. So this will be our data structure for uh, LRU, for LRU. So now let me walk through this code. We have -1, we have -1. Then the first value is this. Is it present in map? No, it is not present. So first create a node and attach it here. So for node I will create a node. So first create a node. So I've created a node. -1 and also add here, also add it here. So first let's complete this. Yes, we have completed. Then we have an list and our map. That's it. We have get and put function. We have get and put function. Get function is pretty simple, but put function is little bit tricky. When our map reaches its size, we need to also remove it. So put function is a little bit complex as compared to get. So we have put this node. Then we have 2 3. So I will add on the head. I will add on the head side. So 2 3 will look like this. A connection here and a connection here, and also add 2 and 3. Then we have 1 and 5. 1 and 5 is 1 already there. Yes, 1 is already there in our map. So directly get this value. We can get this value. So get this value and call remove function on the doubly linked list. Call remove function on the doubly linked list. So we will remove this node. We will remove it. So we have removed it. And 1 and 5, first of all, update this. We have updated our node. Then append it here. Append on the head side. So 2 3. We have 1 5 2 3. Yes. Then we have 4 5. Is 4 there? No, 4 is not there. Is 4 into no, 4 is not there in our doubly linked list. In our map, 4 is not there in our map. Then is our doubly linked list or our map reaches its full capacity? Capacity is only 2. Yes, map reaches its full capacity. So we need to remove a node. How we will remove? The LRU node, least recently used item. We have a function for this. Do you remember? We have a function remove from tail, and it will also pass me a node. So we will directly call this function. So that's why building function is very helpful. So we will directly call that function and it will remove that node and give me a node. So I have this node. Then this is the key. Using the corresponding key, also remove it from your map because the node is now removed. So also remove it from your map. So we have removed it, but we need to also add it. The value is 4 and 5. Add on the head side. First create a node and add on the head side. 4 5. And this we have added on the head side. Also add it here. also add it here, yes. Then we got 6 7. Is 6 7 there? No, 6 7 is not there in our link list. We cannot access this link list. If we can access it, yes, we can access it, but it will take order of n. So using the map we can easily access it in order of 1. So that's why map is helpful also. We got 6 7. Is 6 there in our link list? No, 6 is not there. So we need to add it. But before adding, we need to check, is our link list reaches its full capacity? Map size is 2, it means doubly linked list size is also 2. The full capacity is 2. We have reached its full capacity, so we will remove a node. We will remove the node from the ending side, from the LRU. So we will call our function and it will give me this node and also remove it from its position. So we got 1 5. Using this 1 we can also remove it. Yes, this one, LRU code is complex, but you will get it if you try to understand, and if you dry run this you will get it in the end. So we got 6 7. We need to add on the head side 6 7 4 5. Also add 6 on your map. Then we got 4. Is 4 there? Yes, 4 is there. 4 is there. 4 is there. So using this 4, we have this linked list, we have this node, and we only want the value. Map contains 4, linked list contains 4. We only need the node value. So we have node, just return the value. But before returning, this is the latest item that we used. So 4 5 will now come ahead. Also change its position. 4 5 will now come ahead. So we have accessed it. Now we got 1 2. Is 1 2 there? Is 1 there? No, 1 is not there. It reaches its full capacity. We will call linked list function 6 7. It will give me this node, this key, using the corresponding key. Just remove it. We got 4 5 only. 1 2 come ahead. Then we got 4 5. And also add here 1 2 1 2. Then we got 3. Is 3 there? No, 3 is not there in our linked list. 3 is not there into our map. We will return -1. So we got these two functions. If key does not contain into our linked list or our map, directly return -1. Or first create a node. We are getting it. Yes, we are getting it. So get the corresponding node from the map. This will be our answer. Node value will be our answer. But before returning the answer, we also need to put that particular node on the head side. So first remove that node and add on the head side. Then return the value. Get function is just 4 to 5 lines. It is pretty simple, but put function is a little bit tricky. We have some more conditions. First, create a node. We have created a node. If our linked list already contains that key, if linked list already contains that key, what we'll do? We already have that node. Get that node, get already contained node, then remove from the map. Why we are removing it? Because then we will add on the head side and also put on our map. Remove already contained value from the map and from the linked list. From the map and from the linked list. So we have a remove node function. It will remove from the linked list, and remove function will remove from the map. So whenever you are adding or removing a node, just keep in mind that you have to remove it from the doubly linked list as well as from map. So this is our else if condition, not if condition. This is our else if condition. If it is already contains, then we are good to go. If it reaches the size, if we reaches the map size, we have reached its full capacity, then we need to remove that particular node from the last, from the tail side. So this is the function remove from tail. We are getting the last node, also need to remove the last node from our map. So last key will be removed from the map. That's it. We have removed it. Now it's time to add. So we need to add to head and also put key and the corresponding node into the map. That's it. This is our full function. And the main thing is this if and else if condition. If let me explain again. If map already contain that key, get that key, remove from that position. This is the latest item that we used, so we need to put on the head side. If it does not contain, if it contain, we are removing it, but if it does not contain, we need to put a node. We need to put a node. So if we write it like this, it will give me an error because if let's suppose the map contains a key, so it will hit this condition and remove it. But if map does not contain that key, so we need to run this code. So I did a mistake here. You can write if condition here, but the mistake I did is I am removing a node from a map, but map contains integer, so I have to write dot key here. And this is the mistake I did. And you can write if condition here, no need to require else if condition. Now let's run this and let's find out. So it's saying that we need to write static. So this function is static. We need to also write static. So just write static here, and key is removed. So just write key. Now let's run this. I hope it will work. Yes, it will work. Let's submit this. And in between, let's talk about time and space complexity. So we have this add to head function. It will take order of n. We have this order of n. We have this order of n. So in the get function, it will take order of n. My mistake. It will take order of 1. This is the constant. This is constant. Removed from tail. Remove node is also constant. Then the get function. This line is constant. Then everything else is constant. And this creation, this if condition, everything will work in constant time. So overall, the time complexity is constant, but space complexity in the worst case it will be order of capacity. And time complexity order of 1 and space complexity is not order of 1. Space complexity is order of capacity. And I think this is the mistake. This is the most optimal code that you can write for this LRU problem. And that's it. And yes, I was right. Let's find out in the editorial. The most optimal code will do the work. The get function will take constant, put function also constant, but space is order of capacity, as I already told you. So here the space complexity is wrong, mentioned wrong, and that's the correct space complexity. I will provide you the code in the description box. In the description box you can check that out, but I highly suggest you to write your code on your own, so then only you will understand the logic behind LRU cache. That's it. If you like this video, give it a thumbs up, subscribe to this channel. This video is a bit lengthy, and that's it. Thank you all for watching.